Hello, everyone. Really excited to be here and excited to talk about this topic, which I haven't spoken publicly about before, and it's one of my favorite new topics in JavaScript land. So this is me when I'm not working on computers. I work for Sauce Labs. We have automated web, mobile, and JavaScript unit testing cloud platform you guys might have already heard about. And there I work on our ecosystem and integrations team, which is a pretty cool team. Basically, we're trying to take a degree of stewardship over the open source ecosystem that's around Selenium, Appium, automated testing, JavaScript unit testing, so on and so forth, just to make that open source ecosystem a little better. So I get to spend my days writing open source code, which isn't inherently better or anything, but it's a lot of fun. So we're going to be talking about asynchronous control flow today. So what does this mean exactly? Let's first kind of break down the pieces so we can understand where we're at in this talk. Understanding what async is easier, I think, when putting it into the context of synchronicity, which I think we all kind of know about. Especially after Philip's talk yesterday, we have a good understanding of how JavaScript works and kind of the differences between synchronicity and asynchronicity. Sync code is blocking. There's just a single thread that everything happens on. It kind of executes and returns its result immediately. You get the result from a function. You can assign it to a variable and do something with it right away. And you can handle your errors using try-catch, which is kind of the built-in error handling method in JavaScript. So async is totally different on all these counts. First of all, it's non-blocking, so it's you call your asynchronous function and the function executes, but then you're probably doing some work somewhere else that's not on the main thread. So your spinner can keep spinning. We have what I'm calling deferred execution. I'm not sure if this is the right term or not, but basically you're not getting the result of your function immediately. You're having to wait for it. And so because you're having to wait for it, you can't assign the return value of your function to anything because you don't have a return value yet. So you typically, especially with things like Node.js, you get your result and your error in a callback function, and that's how you do things with them. So here's some canonical looking synchronous code. If you run this, when you're reading your file during that period of I/O, you'll be blocking the main thread of your application. But when it's done, you'll get the data from the file into this variable D. You can console log it. If there's an error in this, you'll go into the catch block. The equivalent in async is calling the async version of read file and kind of scheduling something on the event loop so that you eventually get called back with an error if there was one, or the data from the file if there wasn't, and that's where you can handle the error or do something with your data. So that's asynchronous. What about control flow? Essentially, it's ensuring that your code is executed in the order that your application logic requires. So some functions obviously need to be done before other functions are called. That's how things work in this style of programming. Something like Prolog, I guess, would be very different. So in JavaScript, control flow is mediated by these things called control statements, which are most of the keywords of JavaScript that you have learned when you first learned JavaScript, probably. Things like if, then, for loops, while loops, try, catch are also, I think, control statements, switch, some lesser known ones like break or continue, which can also be really useful in looping contexts. Return also can be a very useful control statement sometimes. So here's a little toy example that doesn't do anything particularly useful, but it just kind of illustrates the concept of dependencies in your control flow. So the first two statements set up some variables. Then we have an if statement. And so the if statement itself runs some code, which is a comparison. And then based on the result of that comparison, we branch and do one of the two blocks. And then importantly, after each of those, either one of those blocks is executed, we then come to the x++ line, the final increment. And these things happen in this particular order. So we can draw little arrows that kind of show the dependencies between these things. Or we could look at something that's more like a real dependency graph, where you kind of have this branching with the conditional and then back again to the x++. But importantly, that final line is really dependent on everything else that happened before, because in this toy example, this is how we decreed that things needed to be. So this is pretty easy to understand control flow in this synchronous context. But what about asynchronous contexts? It can be a little more complicated. So let's say we have this dependency requirement for a toy program. And it's the same as the last one, only we've made the different things that happen as if they were asynchronous functions now. So instead of actual assignments of variables and actual incrementing and decrementing of variables, we've created these toy functions that we're saying are asynchronous. So they take callbacks or whatever. But this is still the desired program flow. We still need these things to happen with this kind of dependencies between them. So how can we write this with asynchronous code? Well, the naive approach might be to write some code that looks like this, basically the same as the code that we had before, the same structure and everything. Of course, this isn't really going to work. What does this actually do for us? Well, instead it does something like this, which is kind of even hard to depict in this fashion. We're firing off all of these functions in the same spin of the event loop instead of waiting for each one to complete, because now we're saying they're asynchronous. So a lot of crazy things could happen here. And this is the source of a lot of bugs in JavaScript programs. When you don't understand asynchronous control flow, you get weird timing issues. You get things that are undefined when you maybe think they're supposed to be defined. It can be a mess. So back to our desired structure for this program, how can we do this with asynchronous code? Well, as you guys probably already know, the solution is to make sure that anything you want to happen after an asynchronous function has completed its desired behavior is to put it in the callback for that function. So basically, it just means that anytime you need something to happen after something else, you have to put it in callbacks. And so you end up with callbacks within callbacks. The worst thing about this example right here is you'll notice that our last desired behavior, which is increment x here, we have to put it twice because there's two ways to get to it. And in each way, we have to make sure that it's in the callback of the path that it came from. So we're now adding a bit of duplication to what before was a very simple set of statements. So let's talk a little bit about some more problems that you can run into when using asynchronous code with callbacks, like in these examples. So something that people talk a lot about, which is more of an aesthetic thing than anything else, is the visual unreadability when you get lots of anonymous functions being chained into callbacks. So this is something that you might find in a lot of code, and it's kind of ugly. Code keeps moving right, and you end up with a bunch of these crying mustache faces or whatever it was that the person said yesterday, which I thought was great. It's very easy to lose track of where you are, especially if we added some logic in random functions here. You might not know where you are in this entire stack here. Second problem is that error handling can be a little cumbersome. So the previous example, we didn't do any error handling. So let's say we had this callback function. It's typical in writing Node applications to have some function which kicks off a chain of asynchronous functions, and it handles all the errors or the final result from that chain of functions. So let's just call it CB for callback here, and we're handling an error or outputting a value. So then we come back to our chain that we had before, but since each of these are asynchronous functions and they have to return their error into the callback, we end up doing something like this to make sure that we can break the chain of asynchronous functions whenever we get an error. So this is really, really sad to have all this duplication around all the time. Conditionals are also a problem, as we've already seen. Another example I'll just go through really quickly. Basically, in synchronous code, you could do something like this, where you have a conditional that, if true, modifies a variable, and then you go on to modify that variable again. But either way, you're going to execute that last line. And as we saw before, you have to kind of duplicate some code in order to make this work asynchronously. And if your code's reasonably complex, you probably end up with a lot of these like next functions or things like this that are, I think, obscuring what's actually going on by putting it into this oddly named next function so that you aren't repeating yourself all over the place. We also need to remember to break out of if statements or use an if-else pattern when we needed neither a return nor an if-else in the synchronous version. So it looks like this is just a little more complex. Even if we can find a better way to do it, it's always going to be a little more complex. And then we have loops as another example. In some synchronous code, we could take some objects, a list of objects, iterate through them, transform an object, or get a transformed object, I should say, push it to another list. This is like map. This is re-implementing the map pattern. Asynchronously, this is a bit more complex. Again, we can't do it using a loop because we need to make sure that things happen inside the callbacks of the previous asynchronous function. So if we used a loop, they would all operate. They would all get kicked off in the same spin of the event loop, and we would have possibly undefined behavior. But we have to check some weird conditions, and ultimately we have to resort to a recursive approach to this. There's nothing wrong with recursion in general. It just doesn't strike me as the simplest way to iterate through this list. Now, maybe if you're from a functional programming background, you'd take issue with that. But anyway, it's not the typical JavaScript for loop that we learned when we first learned JavaScript. So anyway, you could also say that, well, a lot of what I just showed isn't what your application code needed to actually look like. There's a lot of boilerplate, a lot of ways you can abstract this to make a much cleaner way to do the same things I talked about, but still using callbacks. And in fact, there are some great frameworks that help you with that. My favorite in this genre is Kaolin's Async Framework, which is a pretty great helper library for callback-based async control flow. It gives you some really nice methods like series, each series, whilst, or until. They take sets of asynchronous functions and do the control flow logic for you behind the scenes. But interestingly, they're each basically re-implementations of standard JavaScript statements. So series basically stands for semicolon. So in Sinc JavaScript, you just put one statement after the other, and they go in that order. But you have to use series with the async libraries. Each series is kind of like a loop, a for loop, and whilst is like while, obviously, and until is like while not. So it seems like this is about as good as we can do with callbacks, is creating a really clean new API, which is an abstraction over this asynchronous control flow logic. But can we do better than rebuilding JavaScript control flow statements on top of JavaScript? We already have them in the language, right? OK, so let's shift gears. What do generators have to do with any of this? Because that's one of the things I talked about in the title of the talk. Well, generators are a new ES6 feature available already in Node 11 if you pass, I should say 0.11, and up if you pass the Harmony flag to Node. And there are some ways to get this to work in lower versions of Node by using some transpilers. So what do generators do? Well, as we saw in a brief example yesterday, you can use them to lazily construct infinite sequences, which can be useful and very interesting, especially if you like the Fibonacci sequence, which is what everybody seems to use this to do. I've had so much Fibonacci, I don't know if I can ever see another example. So I didn't put one in here, thankfully. More interestingly to me, anyway, code in generators can actually interact with code outside the generator. So this isn't true generally of functions in JavaScript. Normal JavaScript function, once you kick it off, you can't interact with it until it's done doing whatever's inside the body of the function. Then it returns, and then, well, you could call it again, but you can't have a conversation with the function while it's being executed. With generators, you can. And the way that this is done is with a new keyword that's been introduced, which is yield. So here's a little toy example. For the sake of time, I'm not going to go through and really unpack this, but I'll put these slides up really soon so you can work through this at your leisure. But basically, what you need to see here is that we have a generator function defined with a star, and when we call it, it doesn't begin executing immediately. Instead, we get an iterator object as the return value of calling the generator. And that iterator object has an important method on it named next. And when we call next, that's how we can actually essentially step through the generator with yield as a kind of breakpoint or something like that. But next doesn't just step through. It also gives us the ability to receive data or values from the generator and to send data or values back into the generator. And the way this works is a little tricky to wrap your head around when you first take a look at it. So I encourage you to maybe come back to this slide and see if you can figure out what the pattern is here. But anyway, the main insight is that if we can modulate the execution of a generator function based on this external function next, which we can call from anywhere else in our code, then it strikes us that we should be able to use yield to model waiting for an asynchronous function to finish doing whatever it's doing and call us back. So that's exactly what my project Monocle JS does. Monocle JS is kind of a rewrite of this other Monocle, which was written in Python by one of Sauce Labs' co-founders, Steve Hazel, and his brother. They wrote it on top of Twisted and Tornado, which are the kind of Python equivalents of the event loop, I guess. They essentially bring an event loop into Python so you can do async stuff in Python when you could just use Node. So anyway, this is what a very simple program might look like. You kick off your initial generator using monocle.run, and there's a couple other ways to do this as well. But we log a date, then we sleep for 500 milliseconds, so this is like set timeout. We sleep for another 200 milliseconds, and then we log the date again. And you can see in the output, which is actually something that I copied from the console, that we have waited about 700 milliseconds between the first console.log and the second console.log. We don't have any anonymous functions. We don't have any callbacks. Instead, we've just yielded sleep, this calling the sleep function. So this is a kind of general pattern. In regular callback-based asynchronous JavaScript, you have a function. You can pass it some parameters. The last one is always a function, which is treated as a callback. The callback receives an error as its first parameter and any results as subsequent parameters. And then within that callback, you do the things that you need to do. But with Monocle, it looks a lot more like Sinc code. Instead, you yield the asynchronous function along passing it whatever parameters need to be passed to it. And the result, whenever it's done doing what it's doing, is passed through an assignment. So you can capture in a variable that way. And if there are any errors, they're thrown in this general context as an error, and you can try and catch them. So in this expression, what is async function? Excuse me. When you yield async function, what does it actually mean? It can't just be the exact same thing as the original callback version of async function. Otherwise, we'd be calling it without a callback, and it'd result in some undefined error when async function goes to try and call its callback. So async function here is something that in Monocle is called an O routine. It's kind of a Monocle-style async function. And it could also be a function that returns a promise object if you like promises. So you could actually use promise libraries out of the box with Monocle too. So a little more about O routines. This is how you define an O routine. First of all, you get the little helper wrapper function, which is a monocle. If you look at it, it's kind of like a monocle, if you get it. And it's kind of better in Python because decorators look like an @ sign, so it kind of looks like an I inside of a monocle. But anyway, this is the best I could do in JavaScript. So you wrap a generator function with this little decorator. And then inside of that, you can yield to other O routines or promises, as we said. So brief word on the way we use yield. In generator functions, you often think of it as yielding up. Like if you yield 5, that means you're giving 5 back to whoever called you. When using Monocle or something like this, it's better to think of it as yielding 2. Like when you're in traffic and there's a yield sign and you need to wait for something else to happen in order to keep going. So essentially thinking of it as yielding to some asynchronous function. So yeah, just another example. You're yielding to async function, getting the result in res here. So how do we actually turn regular node-style callback functions into these Monocle O routines? It's actually really easy. We have another little helper wrapper for that. So fs.readFile, for example, is a regular node-style callback-based asynchronous function. We can just wrap it in this O_m thing, which you can rename if you don't like that convention. And then now async function is an O routine, which we can yield. So we could use readFile in a sync-like way. As I mentioned before, error handling is done via try-catch, just like regular JavaScript. What's really nice about this is we can now do error handling over entire groups of asynchronous functions. So if any of these fail, we'll break out of the list of statements wherever we're at and fall into the catch block. So we don't need to worry about error handling each of these individually the way we do with callback-based asynchronous functions. So essentially, what this enables us to do is go back to using the built-in control statements we're used to in synchronous JavaScript. So final example, conditionals and loops are super straightforward in a way that in the callback-based asynchronous flow control, it wasn't. So this is very easy to read and understand. The only thing you have to remember is to use yield when you're trying to run an asynchronous function. If you didn't, things would go wrong, which is kind of like if you forget to call a callback using a regular callback-based function. So in some, Monocle JS is a project that lets you write async code as if it were sync code, but it doesn't block because we use generators and the new yield keyword. Few qualifications, though. I know that these discussions, control flow, callbacks, promises, generators, blah, 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 can often bring out the flame in the best of us, but I don't think that it needs to be that way or should be that way. My colleague at Sauce, Emily, said this. I'm right about a lot of things. Thanks, Emily. Which probably means that it's OK if I'm wrong about this one thing. Yeah, that's probably OK. And then in typical Emily fashion, she says, I don't want to generate any controversy here. I'm sure we can iterate on the idea and make it work for everyone. So plenty of puns for everybody here. In some, there are lots of ways to write good JavaScript code. Monocle has advantages and disadvantages, like every other approach. But if you write code with a lot of async functions that you need to happen in serial, it might be worth a look. Also, after Michael's talk this morning, I checked out the Co library that he mentioned that TJ Holloway has been working on. And it looks like it might be exactly the same thing. So if you like that, he also has a lot more stars on GitHub. So if you want to use his thing, that's fine. I just like this approach and this idea. And hopefully, either way, I've done a decent job at explaining kind of the theory behind this approach and how we can use generators to do async control flow in this new way. And whether you like even the generators or something else, it'd be a good idea to educate yourself on good habits of async control flow to make sure you're not introducing bugs into your application. So to that end, I have this repo that I'm trying to popularize that tries to include a bunch of different approaches to asynchronous control flow, callback, Kale and async. The Bluebird promises guy has a thing in there. So please help us augment this to kind of have one place where people can go to learn how to do async better in JavaScript. All right, thanks a lot.